To really be capable of applying machine learning in real life situations, we need to understand not only how the technology works and how to apply it, but we also have to know when it works well and when we should apply it, and when it doesn't work well and when we shouldn't apply it. To that end, we're going to focus this lesson on situations where machine learning can work well and situations where it doesn't work well. Let's start with discussing what machine learning can do well. And we have to caveat this with the fact that machine learning really can only work well if it's given a sufficient quantity and quality of data. If we don't have enough data about the specific problem that we're trying to solve, or our data is not clean and we have a lot of noise or heavy outliers or missing data, we're not going to be able to make machine learning work well, even if it's a simple, straightforward task. So let's assume for the moment that we have sufficient quantity and quality of data. Some of the things that machine learning is particularly adept at include the automation of straightforward tasks, making predictions by learning input and output relationships, and personalizing services or products for individual users. Let's talk a bit about what each of those means. First of all, automation of straightforward tasks. So examples of this might be automation of mail routing based on optical character recognition. So as mail comes to the post office, it's automatically sorted and filtered and sent on its route based on machine learning that recognizes handwritten words and digits and automatically can route that mail to its destination. Another example of automation of a straightforward task would be auto transcription. So when I teach here at Duke, all of my lectures are recorded through the webinar software we use called Zoom. Zoom includes an automatic transcription feature so that after every session, I can receive a written transcript of my lesson, which I can then post up and make available for my students. Zoom uses a machine learning model behind the scenes to automatically transcribe my speech to text to provide me that automated transcription. The second thing machine learning can do particularly well is making predictions by learning simple input-output relationships. Examples of this might include predicting demand for a product based on things like time of day or season of year or temperature outside. It could include things like predicting grades for students in my class based on how often they show up to class, whether they do their homework or not, and their quiz scores throughout the semester. Finally, personalization for individual users. So if you're a Netflix or an Amazon Prime subscriber, for example, you should be very familiar with this. Netflix provides personalized recommendations of movies to watch to users based on the machine learning model. Likewise, many of the online retailers today use machine learning models to recommend products to buy based on your buying history and the buying history of users who are similar to you. So now let's talk about some of the things that machine learning cannot do very well. The first is understanding context. So a good example here would be machine translation. As humans, we have the capability to understand context about conversations that we have. We can understand when a sentence is intended to be a joke or when someone says something that is intended to be sarcastic in nature versus taken literally. Machine learning models today are unable to understand things like jokes or sarcasm. So everything that a machine learning model hears, it interprets as a literal statement. Second thing machine learning cannot do particularly well is determine causation. This is really important to understand that machine learning identifies patterns and correlations in data, but does not determine cause or causation, whether one thing caused another thing. So to take an example of this, we could show that over the course of a year, ice cream sales and violent crimes are actually correlated. So as ice cream sales go up, violent crimes also go up. This is an example of correlation between two things. However, it would be obvious that ice cream sales going up is not a cause for violent crimes going up. There's other variables that come into effect, things like seasonality and weather. It can be shown that in summertime, demand for ice cream goes up, but violent crimes also rise in the summertime. So if we were to build a machine learning model, we would identify a strong correlation between ice cream sales and crimes. But we have to be careful not to misinterpret that correlation as causation. Third thing machine learning cannot do particularly well is explaining why things happen. So machine learning again identifies patterns, but doesn't attempt to explain why these patterns are occurring. It can explain outputs in terms of correlations with given input features. But again, it doesn't explain why this combination of input features results in a certain output. And finally, machine learning is not capable of determining the impact of what we call interventions or possible solutions on a problem. It's also not capable to find solutions to a given problem. Let's take an example of this. Suppose we were building a machine learning model that predicts crime. It's likely that we would be able to accurately predict crime given a certain number of different features, things like location, seasonality, and other factors. We could build a model that could effectively predict crime, but this model wouldn't necessarily tell us anything about how to reduce the crime. So for example, if we wanted to analyze whether enacting a law to ban guns in a certain area would reduce crime, our machine learning model that we've built really wouldn't be able to tell us anything about whether that was a good or bad solution and how that might impact the predicted crime. Likewise, our machine learning model wouldn't be able to answer the question, what should we do to reduce crime, or to suggest or propose solutions to the problem that we're trying to model.